sure I've got everything up and running. Hi. I just wanted to give a quick shout out and say thank you to Barrier Piggies for inviting me to come and speak, and to LinkedIn for hosting and feeding everybody. So how many of you guys have a phone that tells you when you're running late to a meeting or running late to get to a location? Yeah, you guys have Androids, don't you? How many of you guys talk to your phones? Okay. Yeah, I know. Some of us are still on the fence on the whole talking to the phone. How many of you have taken a photo and noticed that it autofocuses on people's faces when you take a photo? All right. So all of that has a neural net or neural nets integrated into the programming when you are doing any of those things. And so I was asked to come because I put together a talk on neural nets for newbies, my kind of funny little phrasing. But primarily it was my way of trying to give an introduction to what neural nets are. Neural nets are, at the heart of it, an equation. And they're very complex, and they can seem a little daunting when you start to look at them and try to get an understanding of how they work. So, you know, I've seen a number of presentations on them, and they're definitely getting better, but I think for those who are not as steeped in the math space or steeped into, you know, just algorithms in general, they can seem a little almost overpowering, and I wanted to create a presentation that was kind of an intro, a way to make it feel a little easier to get into the space and give you something to build a framework off of. Now, I've given this talk already. Some of you may have seen it on PyCon, so I am going to be primarily going through what I went through before, but I'm going to try to provide a little additional context tonight. And really, the talk is to give you a little bit of a backstory around what neural nets are. It's to go through some math and some of the structure at a very high level to give you, like I said, some fundamentals and a framework to work off of. If you're rolling your eyes and you're thinking, math, ugh, I hate that, you really need to kind of get over that if you want to be serious about getting into neural nets. I mean, you really have to. I'm glad you guys appreciate that. So systems engineering is also kind of an important component to being able to be realistic about applying neural nets. And I'm going to just touch on why that's important. And then I'm going to show you just a little bit of code and give you a list of packages that you can further explore in terms of Python packages, because I know we're all Python people. And then also give some context around deep learning. How many of you guys have heard of deep learning? Yeah, it's a very hot, sexy topic. Just like, you know, data scientist and machine learning. Everybody's doing it. It's all the rage. So I'm going to try to help to sort of put some context about what exactly is deep learning. And then I'll give you some references and just tell you a little bit about what I understand is sort of the next steps from neural nets. I don't expect you to walk away from this talk understanding everything about neural nets. It's just, there's no way I could cover all of that within the next 30 minutes to an hour. I want you to be able to walk away and have an understanding, if you don't know anything about neural nets, or even if you do, at least an understanding of how to go forward and further research this yourself and look at how to find out how to do these things going forward. So let's talk about what they are. Neural nets, the idea was born off of trying to model our brain. Now, at a very high level, our brains have a bunch of neurons that are connected with synapses. If I touch my cheek, there's some neurons that are firing and interpreting this data and sending out signals through the synapses to other neurons. Now, yes, it's extremely abstract. There's a lot more technical terms and chemicals that are going on in your brain that I'm not going to try to explain or define. But at a very high level, that concept of having these neurons and these synapses and data being sent and transferred and interpreted was really what inspired the neural net structure that we see in technology. But as I said, neural nets, you know, at the heart of it, that's an equation. It's an algorithm. It's an algorithm that's part of the machine learning family. Machine learning is all about algorithms that are for prediction and classification. So neural nets are part of the machine learning family of classification and prediction. They're a very complex part. They're very, you know, detailed, can deal with some pretty amazing patterns that most of the other machine learning algorithms can't deal with. But they're not necessarily the solution you're going to use for all your problems either. So where did they come from? Technically, there was a couple of guys back in the 40s who, you know, were looking at how to design your brain with electrical signals with, oh, I'm forgetting the terminology, but basically they came up with this methodology looking at the way you pass electrical signals through like logic gates and so forth. They designed it out, and then when the 50s came around and computers started to come onto the scene, people used that methodology and said, hey, let's try to put this brain structure into our computers. And really it comes down to creating an algorithm inside the computers that can interpret signals in a certain way that's like your brain a little bit. But everyone heard, oh, it's like our brain, so now we'll have computers that can think like us. You know, there's so much excitement and so much hype at the time around what neural nets were able to do. And it was unfortunate because that hype was so high that the expectations, it was hard to meet those expectations. There was a lot of failed experiments, significant amount of money went into the field, and then they just didn't really see the value out of it. You were able to run some neural nets back then. There was a couple that were actually generating some real value in the commercial space. There was one that was used actually to reduce, I think it was like echoes on the phone line that's still in use today. But really, the actual value was so limited back then. The ideas were very much on the right path, though. It wasn't until probably about the 90s that we started to see some, I think, more real-world actual value out of these neural nets. Jan LeCun did some research out of AT&T Labs, and he specifically was focused on trying to classify handwritten digits from 0 to 9. That now is known as the hello world of neural nets when you're starting to work on a neural net. And that's why I have the MNIST. And I'm not going to be able to tell you off the top of my head what that stands for, but you can look it up. Anyways, Jan LeCun created what is called the convolutional neural net. That's a type of neural net. I'll come back to that. But that was around the 80s and the 90s. But it wasn't until literally in the last 10 to 15 years. And this was a paper that Jeff Hinton, who is based out of Toronto, and he's kind of known as being one of the real kind of visionaries or leaders in this field in particular, but he had coined the word deep learning, or words deep learning, back in 2006 with an actual structure he was able to prove had real world value in terms of why you would use neural nets. So that's kind of just a real brief backstory. And what's really crucial to understanding why we're seeing value now, I think it's kind of obvious, is that we've had an exponential rise in our computational power. The ability to hold information in memory, the ability to compute and actually process data in our computers has significantly improved since the 50s. And neural nets are really hinge on that to be successful. And the reason why is because of how complex their structures are. So I'm going to get into that a little bit more, but before I do, to give you a little more context, I've already given you some examples of what our neural nets used for, but they are behind a lot of the interesting and very difficult problems to solve when it comes to like language processing or image processing. We're especially seeing it focused around natural language processing and speech recognition, or facial recognition. Some of it's a little kind of scary when you think about what the government might be doing with it. Some of it's kind of interesting when you think about how Microsoft recently came out with some research where they're in real time actually having, I think when you talk, it's actually being immediately interpreted into Chinese. And this is due to neural nets that they have built out, or a structure using neural nets that can do that kind of processing. It's pretty amazing. You know, we all know that the self-driving car is coming. It's only a matter of time before it takes over our freeways. Some of you may have heard of the recommender engine with Netflix, the winner of the Kaggle competition a few years back. That actually incorporated a neural net structure. Neural nets are actually playing more and more role in recommender engines and ad placement, actually. And it's because they're much better at doing some interesting nuanced perspectives on, you know, taking the amount of data that's out there and looking at how to really classify it. So, and then the other thing I was going to mention about those spaces in particular is that why neural nets are having such an amazing impact, outside of the fact that our computational power is so good, is that we can throw more and more data at it and get increased accuracy. So the more data, the better the accuracy in those types of fields. The data needs to be rich. The data needs to have layers to be able to have value. And that's where other algorithms will start to tap out. Now, like I said, neural nets, you shouldn't say, oh my gosh, you know, it's solving these really interesting problems, and if I throw more data at it, it gets better. It's not true in every case. There's definitely many situations where you take samplings of data and you can get some real good value, or real, my words are so good today. You can definitely have some very significant performance from smaller sample sets and with certain machine learning algorithms. So don't look at neural nets as being like your hammer and you're going to go look at every single problem and start to hit it with that hammer. All right, so let's talk about the math of neural nets. When I gave a talk about machine learning, I actually tried to center everybody around linear regression, which is the beginning algorithm that you really would start out when you're looking at machine learning and how to apply it. So this is linear regression. This is definitely not neural nets, but I'm using this as a way to set some context as we dive into the math around neural nets itself. Now, in the scenario that I have up here, basically what's going on is I've got 2 dimensions of data, and I'm trying to predict it with a line. Now, you could argue that maybe this kind of data shouldn't be predicted with a line, but you know, that's not what we're here to discuss. You all know that an equation for a line is y equals mx plus b, or I'm assuming most of you have heard of that before. And that the m and the b are the coefficients that help you determine how to apply that line to this set of data. A couple things I'm going to note. This is supervised learning. Where we're seeing the most value for neural nets in general is in supervised learning. So that's why we're going to focus most of our conversation around that. So it's supervised learning because we have actual data that is labeled, that has an actual, like, we know what the results should look like. And we're going to apply this equation and create a model for this data set. And the way we create that model is finding the best, most optimal coefficients. And our objective is to get the least amount of error from all of these real representation of data that we have. So we're going to go and do the line, calculate the error, and keep iterating until those coefficients are the best representation with the least amount of error in terms of this line fitting this data. That's kind of the heart of any type of equation that you're trying to do in machine learning. And that's really the heart of what we're going to do when we work with neural net. So when you start with a neural net, the equation at the heart of it will be on a neuron. So you have one neuron, and in that neuron you're taking in some inputs and you apply weights. And then you sum that together and you pass it through another equation, which is called the activation function. Now, the inputs are going to be depending on the kind of data that you're processing and you're sending into the neuron. The weights are your coefficients. And the weights are something that you will have different ways that you might initialize them. There's a number of methodologies and approaches that are out there that you can look into, but usually they're done in a random sort of fashion using different types of distributions. But your weights are your coefficients. You apply weights to the inputs, you add those together, and then, as I mentioned, you apply an activation function. And those are also, like I said, different types of equations. This is just a couple of the activation functions that you can choose from. There's a number of them out there, and I highly recommend looking into them and why you use them and when. But the activation function is basically processing the result from the inputs times the weights that are summed together and determining, is this neuron going to send a signal or not? And you use the activation function, as I mentioned, based on the type of data and the type of problem you're trying to solve. So what does that really mean? You're like, okay, numbers, or there's symbols, and what is really happening there? So this is a very abstract perspective on that equation. But when I gave the talk at PyCon, I said, you know, let's say you're trying to decide what talk to attend. And your inputs in this case would be something like, is it a speaker you know about or want to hear? Is it a topic you're interested in? Is it the timing good for you? Now, imagine those are binary, meaning you have a 1 or a 0 for each of those inputs. And the weights are really kind of what's important to you in terms of level of importance for each of these inputs. Again, weights are your coefficients. And so the speaker might be somebody you don't really know anything about and you're not that interested, so it's a 0. The topic is actually something you really want to know about. It's really crucial for your job. So that's a 1. The timing is after lunch, I want to take a nap, so it's a 0. When you multiply the weights times their priorities and you add them together and you apply an activation function, and I'm kind of doing a little hand waving on the activation function, you'll find that you will probably go to this talk because your activation function helps set a threshold of 0.45, and your priority for the topic is about 0.5. So Like I said, it's a little hand-wavy, it's a little abstract, but I'm trying to, or not abstract, but I'm trying to give you a high-level perspective on how to think about this equation and what's going on with this neuron. And what's going to happen with this neuron is it's going to say, go to this talk. So that's great, and that actually is a neural net at the heart of it. But really, neural nets aren't typically just one neuron. And this is also an extremely oversimplified perspective on a neural net structure, but to give you at least an understanding that you typically at least have 3 layers in your neural net structure. And you'll have an input layer, which is the input data that you're going to bring in and process. You'll have a hidden layer, which is where you're doing the processing. That's where you're doing those calculations, the equation that we've already gone through so far. And then the output layer, which is aggregating the results. It's aggregating which of these neurons have sent off signals. And each neuron in the hidden layer has an equation on it. It has different weights on it. And it's sending out signals in terms of, not all of them will send out a signal. Some will send out signals, some of them won't. Something else to note is that not all of these neurons are necessarily connected to the inputs. In this case, in the example I have up here, it's a fully connected neural net. But sometimes you don't have a fully connected neural net. Sometimes only like maybe the first 2 input neurons will actually only go to maybe the first 3 hidden layer neurons. So it's just something as a nuance to think about in terms of these structures. They get really complex really fast in terms of how many neurons are you bringing in as an input, how many neurons do you have in your hidden layer, what are your activation functions, how are they all connected, and then how do they send out, how are they connected to the following layer as your output. And then it gets even more fun because you can layer these things together. So I've talked about layers, then imagine connecting up those layers. And so now your hidden layer can become an input layer to the following layer. And the following layer can become an output layer to the previous layer. And so you're really just sending data through various layers of a net. Now, it can be 3 layers at a minimum, or it can be many layers. And I think it just depends on the problem and how complex the data set is to determine how many layers you will use. Yes, this starts to get onto the deep learning space. Yes, usually you have more than 3 layers when you get into deep learning, but that's not why it's deep. So yeah, you can connect up the layers. But what does that look like? That's kind of abstract. So let me try to break this down into an example with computer vision. So you have an image, and we're going to say we're creating a neural net that is trying to classify images that are Ada Lovelace. And you have this image. You're going to take the image. You're going to break it down into pixels. Each pixel is going to be converted into a number. And you can create a range of numbers based on how gray that picture or that pixel is. It gets even more complex when you add color, but just go with it for right now. We've got gray image, a grayscale image. We convert each pixel into a numerical representation of how gray that pixel is. And that becomes our inputs. And let's say this is a 28 by 28 picture, even though I know it's not technically a square. But pretend it's a square. And if you take a pixel per point in that image, you're going to have 784 inputs, okay? So your first layer is 784 inputs. I do not have actual circles up here representing the amount of neurons that you would typically have in all of these layers, but I'm trying to at least give you some sense of how this flows. So you've got your inputs. They go into the first layer. Now the first layer is going to do an interpretation around a feature type that's probably something like an edge. When you look at things, typically your eyes start to interpret edges in whatever you're looking at. You probably don't know this, but there's been a ton of research about it. And what's interesting is that in computer vision, they find that the neurons in that first layer are actually looking at edges. And so each neuron is unique in an edge that it might be looking at in the picture, in a certain place of the picture. So that first neuron isn't necessarily looking at the whole picture. It's looking at a little point in the picture, and it's looking at an edge at that point in the picture. And it's looking for that edge. If it doesn't see it, it won't signal. If it does see it, then it'll send out a signal. There's a lot more that's going on there, frankly, in terms of how it's analyzing and how it's transforming the data. But I'm just trying to give you just a slice of how to think about this. So it sends out in the first layer, I found these edges. The second layer gets those signals. And the second layer is focused on object parts. The object parts are things like your nose or your eye or your ear. And so each neuron will represent a different nose or a different eye or a different ear. And it'll look for whatever signals come in and say, oh, I got these signals on these edges, so this nose has been potentially identified at this probability. And it'll send out another signal. And then the next layer, let's say, is made up of faces. And if we're specifically looking for Ada Lovelace, we could say each neuron is maybe a different face for Ada Lovelace at a different age. And depending on the signals that come in based on those objects can determine, hey, I found this facial representation of Ada Lovelace. So I'm going to send out a signal and say, I found her. This is Ada Lovelace. Now, this is not Ada Lovelace, although Google did say it was, but it's not. And I did that on purpose. So first off, just trying to give you a sense of how these neurons are potentially looking at the data. It's looking at the data in terms of different types of features, different representations of features. Features can be anything from, ways to slice up that image and how to represent parts of that image. It can be anything from like your demographics, how old you are, where you live. It can be something like the sentence structure, nouns and verbs, and even just letters or things that follow in terms of a sentence. So features are the ways to describe and sort of break out how to group and look at the data set that you're in. And the neural net layers are looking at different types of features within the data set that you're processing. So that's what's going on when you look at the layers. And the reason why I have this not working correctly is because you have to spend some time making it work right. You can create a structure all you want, but it's probably not going to work first time out the gate. If it does, that's amazing. So when you are building a neural net, like I said earlier on with my linear regression discussion, is that you usually are going to use supervised learning. You're going to have labeled data. And part of why we're seeing so much success in neural nets is because we have so much labeled data now that we can get access to. Is it right? Not necessarily. There's some methods that are out there that you could use to try to validate your data, but at the end of the day, to some degree, you're kind of stuck with, I got a lot of data that's labeled and I kind of have to trust there's some error in it. But anyway, you work with supervised data, typically, and that means you have labeled data. And let's say we have all these photos. They've all been labeled with names. So we'll split them out into our test set and our training set. And that's because we want to be able to create a neural net, but we don't want to overfit it. We want to know that we have created a neural net that's applicable to a wider range of data above and beyond the set that we currently have. So we can use it for future recommendations or future classifications of images. So how we make it work is that by the time you get to the end and you get an actual classification at the end or get some type of prediction at the end, you can compare it to the actual data that you have in your training set, and then you use what is called a loss function. And similar to the activation function, there's a number of different types of loss functions. They're equations, and they're ways to transform the data to describe the error. I'm not going to, again, take time to explain all these different loss functions, and there's many than what I have listed up here. It's a similar situation with activation function that, depending on the type of data and the type of problem you're solving, will help determine what loss function you will use. So yeah, I'll leave you with that part. So like I said, you're transforming the data, the result that you have, and our goal, and a goal you usually will be having is minimizing error. Sometimes you'll have a different goal, but we're going with that for right now. Once you've transformed the data, you use what is called an optimization method, also referred to as backprop or backpropagation. And you literally are going to take that error and go back into the neural net and update each of these neurons and update their weights, because those weights are the coefficients. And just like linear regression, you keep tweaking your M and your B, your coefficients, to get that line to fit the data set. You will update each of these neurons' weights to get the neuron and the neurons and this whole neural net to appropriately represent the data. Now, there's a lot of other things that go on here. There's definitely work that you need to do around, I'm sure many of you probably know about regularization, and if you don't, it's a way to try to prevent yourself from overfitting the data. But ultimately, what I want you to understand, you have your inputs, you have one to many hidden layers. Those layers are doing analysis on different types of features within the actual data itself. Each neuron has an equation on it. The equation is typically taking in the inputs, multiplying it by weights, and then it's using an activation function to determine, do I send a signal? When I get to the end, I'm going to look at the actual results that I know I have, see what my error is, and apply a loss function, and then I'm going to go back and update the weights on each of these neurons to help make this neural net fit it more appropriately. You will change the weights differently on each of these neurons, and the optimization method will help you determine how to change the weights on each neuron. The optimization method typically is something like stochastic gradient descent. There's a number of methods that are out there that people use and explore for kind of fixing this neural net. Once you've done it, you can take your test data set when you're doing supervised learning and go back and see, did I actually create a neural net that will accurately predict results that I'm looking for? There's a number of ways you can go through and do your test data set. Typically, people are looking at just straight accuracy. You know, how many did I get right out of how many total in the test data set that I was passing through it? But you can use things like F1 scores or rock plots and stuff, just depending on like what you're working with. So yeah, that's your neural net math and structure at a very high level. Like I said, I'm giving you the fundamentals to help you get started. There's so much more nuance to this that you can really explore in terms of how you build the structure out. So a couple of other things to note about neural nets. I mentioned this a little earlier on. There's a couple of different types that exist in terms of how they're structured already. The main one is feed-forward, and what we've talked through is primarily feed-forward. And most of the ones that exist are typically feed-forward. And feed-forward is really about taking the data and moving it through the neural net, forward through the net. But there's a couple of other structures that exist, or there's actually many different structures that exist, but one of them in particular is recurrent. And recurrent, the idea with recurrent is that it's helping to hold what they call as memory. It's helping you track the timing of data. So you can actually loop data or loop information back into the neural net because of the way the structure is actually built out. This is really great for natural language processing, and it's pretty popular in that space in terms of speech recognition and so forth, because you think about the timing of how the actual sentence structure works. Another one that I will mention, and I'm not going to tell you how it works, is convolutional neural nets. It would take way too much time to explain this one, but the reason why I bring this one up is because it's extremely popular when it comes to image processing. Everyone's talking about this when they talk about image processing. It scales really well. It has a variety of different layers, and there are different types of layers that are going on inside of it, and it's not fully connected on all of its layers, so that's why it can scale really well. But when you hear anybody talking about applying neural nets, and most of them are talking about like the ImageNet projects that are out there and so forth, or the ImageNet competition. They're usually looking at convolutional neural nets. Okay, I talked about this at the beginning in terms of I was going to touch briefly about systems engineering. You know, typically when you're programming, you're not, well, actually I'm not going to go typically. Let's just say this. When you are going to be realistic about actually applying a neural net, and a neural net that's going to have some kind of impact around like images or natural language processing, there's a certain amount of work that you can do on your own laptop, but you really will start to hit some limits there. So the real research that's going on right now is in GPUs. If you want to get serious about applying something and quickly having some results, I would recommend spending some time understanding about graphical processing units. I'm not going to try to explain too much about that beyond GPUs are doing math computations like a CPU, but it's much more optimized, and the way it does the computations is definitely more complex. But the way it's built out, like I said, is more optimized. You're looking at potentially training your nets like 2, 3, 4, 10 times faster than you would on a CPU cluster. It just depends on the problem and the data set. I keep saying that because everything is all dependent on that. But GPUs is where the programming is focused right now for those who are really looking at neural nets and applying them in the commercial space, in the real world, and research in general. If you have heard of GPUs before, you all have them in your computers for doing, you know, graphics on your computers, but they're not the kind of GPUs typically that you would use for a neural net. There are certain types in particular that are specifically geared to them. Typically, it's NVIDIA's GPUs. You may have heard of CUDA that's used to help you actually get stuff spun up on GPUs, and there's like a PyCUDA interface that I've heard about, but I haven't played with myself. They're very popular when it comes to gaming and research in particular. And then other areas that you might want to explore as you get more serious about this is things around just distributed computing. I think just understanding how your memory and your CPUs or GPUs are functioning in general will help you have a better respect. Multi-threading, parallelism. And I was told by somebody out of Baidu that they're really focused on high performance computing in particular. And this is not cloud computing. This is like bare metal boxes kind of connected and having some specific optimizations around actually like keeping your network and your distributed network in the same location, and then how you actually connect it all together. I don't know a ton about high performance computing right now. I just would say that I don't think it's something you have to research right out the gate, but just keeping in mind that that's an area that is currently being explored to help optimize and make the training of a neural net go a lot faster. And that's what this is all about, is training a neural net takes a lot of time. Some people can take, depending on what they're working on, it could take a couple hours, but that's rare. Probably a day or so. A week is what I think most people can tolerate. But some research is going months, maybe years. I don't know. That could be very realistic happening right now. I know that neural nets can create some limitations when you start to look at this type of stuff for getting access to these types of hardware or solutions or systems. I would say that we're seeing more and more access provided to things, especially like AWS has GPUs actually, and I've heard it's not that expensive to actually spin one up and leverage it for your own kind of explorations in the space. So yeah, mixed perspectives on whether it's limiting or not, but I would say definitely explore this if you want to get serious about neural nets. Okay, Python, we're all here about Python. You're like, oh, I gotta research, linear algebra and derivatives to understand neural net structures and just neural net structures in general and all this other stuff. But you can actually start with a neural net today. And I'm not trying to be like a huckster. You can have one too. I am trying to make it so that this doesn't seem like, oh my God, this is too daunting and I can't get started. There are fantastic packages that exist out there in Python that can get you off the ground. Some of these definitely require a little more time and effort to understand neural nets to get started, in addition to understand how these packages actually function. Theano is one that will be really great for you if you want to get serious about understanding the actual mechanics behind a neural net. It's heavily documented, and it's thoroughly used in the research space as well as the commercial space, and it's open sourced. So I would definitely say explore Theano. Most of these packages I've listed over here, or several of them, are actually just wrappers around Theano, and they're trying to make it easier. Debatable about whether it makes it easier or not. This is very much a rough line of how user-friendly these different ones are. I would say that PyLearn 2 is definitely not as user-friendly as I would like to think it would be. OpenDeep is actually an open source solution that, funny enough, the creator is speaking up at Yelp tonight. He's a friend, and I think it's a good solution to look at. And it does wrap around Theano to a degree. But Lasagna actually I think is the one that if you really want to kind of get off the ground and leverage one of these packages would be fun to use kind of out the gate. That is not requiring you to pay any money. Caffe, CXXNet, and Fan, those are actually Python wrappers around C libraries, and they're great at being extremely fast and efficient. Caffe is also pretty popular when it comes to the commercial space. Caffe is literally like a JSON file that you put your configurations into, and then you just pass it into a Python API. So it's really understanding that JSON file and then what kind of neural net configurations you want to pass into it. And then GraphLab. So I don't work for GraphLab, but they do have a good Python solution that you can easily get up and running. And they have some pre-baked structures that actually come back with some fairly decent results on the MNIST solution. So I'm going to show GraphLab, but yeah, it doesn't require you to pay money to explore it. You do have to get a product key and set up in your configuration file. But outside of that, I'd say just play around with it and check it out. It's probably one of the more easier ones to get going. Scikit-learn does have what is called a restricted Boltzmann machine solution. And I don't really want to go too far down the rabbit hole explaining that, but it's really not, it's more for feature engineering. And I would say hold off on exploring that initially. I'd put that in the back burner because it's not as easy to jump into as some of the other things that scikit-learn is providing out there. And then MetaMind is actually, I think they're technically a competitor of my company's, but they have a Python API, and they've got a web GUI interface, from what I understand, that you can literally just go and say, here's my data, and here's the configurations I want. And they also have, like I said, Python API that allow you to kind of plug it into your code. My company does not have Python bindings yet. We are based in Java and Scala, and so I currently work for SkyMind, and we are an open source deep learning solution that is integrating with various types of backends. And I will say, we are definitely not as user-friendly as some of these other products are right now. We require a lot more knowledge to be able to get it up and running, but we're working on it. So yeah, we're not on the space just yet for the Python packages, but I had to make a little bit of a plug. So yeah, Lasagna I would highly recommend to get up and running. Theano definitely spend some time with. And then let's talk about GraphLab, which the other thing I was going to mention about this, GraphLab apparently is a wrapper around CXXNet, just to give you guys a heads up. So that's what I heard from somebody who is very much more in the know on that than I would be. So MNIST, we're going to talk about MNIST for our code example tonight, because it's the hello world, and if you haven't done neural nets before, then you have to start there, from my perspective. If you have done it before, I'm surprised you're here. No. So for MNIST, as I mentioned, the whole idea was taking some images of handwritten digits from 0 to 9 and trying to go through and classify those and create a neural net that will classify them. And just to kind of oversimplify this, you have this image, you break it down into pixels, and you do a numerical representation. You're usually doing a range between 0 and 255 when it's grayscale. I'm just oversimplifying this for everybody to make sure it's clear what's going on. The neural net structure you're going to build out, it can vary in terms of the number of layers, but you can imagine you've got technically you should have about 7 layers, but it can vary. And it's really not going to look exactly like this, but I was trying to marry this back to the whole presentation that I've done so far. Usually when you're doing an MNIST, you're doing some type of convolutional neural net structure, and like I said, that's a little more complex. We're not going down that rabbit hole today. So you bring in the pixels from the image. You're going to use each layer to analyze different features of those pixels in that image. And then at the end, and I think this is something key that I really haven't highlighted yet, but at the end, you're going to have a neuron in your output layer that will represent each classification or each prediction that you're trying to make on that data set. And in our case, we have 10 digits that we're trying to classify. And what's happening is that you'll have like a 1 or a 0 or some percentage that comes out on each of these nodes to say, which one is it. If it's a percentage, you'll just take the max. So we're going to try to make this neural net work so that when we get to the end, this is going to give us a very low error rate on predicting, or classifying, I should say. This is a 4. So to do this, like I said, you need to get your product key in place. But once you do, all you have to do is say import GraphLab, and they have the MNIST at this site. But I will say this, that the MNIST is in many different locations on the net, so it's easy to find. You bring in the MNIST. They have it configured in a way that you can just bring it into their S-frame, and their S-frame is really the same as something like a pandas. It's a data frame. It's rows and columns, and it's basically 2 columns. The first column is going to have all the numbers for the image to represent each pixel of the image. So it's like a big, another data frame probably within that, each cell of that first column. Basically, digital representation of the image. The second column is going to be your labels, 4, 7, 9. So happens to also be numbers, but in this case, it's the labels for those images. And once you've pulled that into an S-frame, the way they've built out their neural net classification class is you literally call neural net classifier and the create method, and all you have to do is pass in that input S-frame, that input data frame, and then tell it which column, what's the label for the column that has the labels in it. So you say, my target, where everything is labeled, happens to be in the column called label. Hopefully that's extremely clear. I tried to make this as clear as possible. Now, there's a number of other parameters that you can pass in here that will help you start to tweak the way this is running and the way you are training this neural net. There's also another class that they have where you can actually make adjustments to their kind of prepackaged neural net structure that they'll give you. I don't have that code up here just because I didn't want to spend too much time on that when I initially created this talk. I do have examples, though, and I'll show you that. Or I have examples out there in the internet that I will show you a link to. Once you've done the model, and actually, let me just go back to this real quick. Once you've called this class, called create, passed in the inputs, and told it what the labels are, it's literally built. It's already got the structure. It's taking the data, it's doing the training, and it's getting to the lowest error rate until the model is at a place where it thinks is adequate for us. And once it's got that model, you can then pass in any new images you want to your neural net. It will run through, and each layer will do different analysis on the features and come back with an actual classification. Yes, it's reversed. I'm not going to tell you why. But this at least shows you a image representation of what is going to go on with that neural net you created when you created model. And so once you have your model, you can also call a method called evaluate. All it's going to do if you pass in your test data set is go through and come back with classifying all of those images with the label and comparing it to the actual labels and tell you how many you got right. And out of the gate, 97% is really good. So they've obviously done some work to make this really work well. Yeah, that's it. Like, you can do this right now, and you'll be like, I have a neural net. That's amazing. Yeah, you have to spend a lot more time really understanding what's happening and why it's happening. But hopefully this at least gets you started with understanding you can start playing around now. And as I mentioned, I created a repo for this talk where I've actually pulled in examples for MNIST into the repo from some of the packages, not all of them, but some of the packages. Tried to do a little annotation and some kind of adjustment to the way the structures ran so you could have an easy way to understand what's going on and where. The things I mentioned in terms of some additional parameters you can pass into GraphLab, I actually have in the example in this repository. So, feel free to go out and explore it. If you want to add to it, you're welcome to. If you want to complain about it, feel free. I might just ignore you, but you're welcome to go out there and complain all you want. Use this as something to help you get started. All of those packages have an MNIST example out there somewhere, so go. It's not that hard to find. There's plenty of examples out there. All right, so last couple of things, because I know that neural nets can be a little. It's a lot. And it's interesting to a point, but it's still a lot of information. Okay, so the last couple things I want to touch on. Deep learning, what is it? All right, so deep learning, bottom line, is automatic feature detection. There's a number of other components that play into deep learning, but when you really get to the heart of what is deep learning and why does it matter, it's the fact that you can pass in raw data into this and come out with some actual features that are important and have value that you really want to use to help you predict and create patterns around that data set in general. Feature engineering is an interesting space. It requires a lot of time and money to get it right because you're trying to find good data representation, good data types to represent the data and the data space that you're working in. And it just can take a lot more time and money than people typically would like it to take to be able to do that and create adequate models. So having a tool that can do this automatically is pretty awesome. Not easy to do, but it is becoming easier as we continue to explore neural nets, the types of structures that are out there, and how to use them for processing things like images and words. So if you don't know very much about automatic feature detection, I would just say look into what feature engineering is, and then you spend some time kind of researching this a little bit, and you'll start to understand it, and I think you will hopefully start to respect why deep learning is so popular for those who are using it actually. It's pretty powerful in terms of actually having an impact. Okay, so I created a list of some of the resources that I thought were the most useful for me when I first started researching this. And this is not necessarily exhaustive, and this may not be necessarily useful for you getting out the gate, but this was useful for me. I also have a number of there's a number of people who helped me, and I'm very grateful for the people who spent some time with me helping me put this together. But I have a number of other resources that I used, and yes, I'm going through this really fast so you can't take a photo, or maybe you're videoing it. So all of that is actually, these slides are all already out there. You can easily get these, so it's, and I'll show you the link in a second. Last couple things I'm going to mention. So as I mentioned, neural nets, the biggest impact they're having, or at least where they're really popular right now, is definitely around feature engineering. That's a pretty significant space for them. Combining models is also kind of a fun, I think multimodal is the term for it. It's sort of a fun exploration space for a number of people right now. There's a lot of research that came out in the fall about combining recurrent neural nets with convolutional neural nets to help describe photos. They got, I think, used Mechanical Turk and had a bunch of photos described, had sentences written up about these photos, and literally have now taken new photos and processed them and come back with some pretty spot-on descriptions. Karpathy is a researcher and a professor out of Stanford who did a talk in February out of Yelp, and it's recorded. It was a really good talk about this, that the research that Stanford did on it. And like, I think Facebook and, Google and Apple and all of them actually came up with papers and research on all of this back in the fall. So it's kind of cool, like what people are starting to figure out what they can do with it. And I think there's more and more exploration about combining different neural net models to solve problems, as well as combining neural nets with other types of machine learning models to solve problems. Use the neural net to get the features, and then maybe use an SVM or a random forest to come back with the actual classifications. Natural language processing, image analysis, or image search are really where a lot of the research is going right now. It's where everybody's sort of centered and focused on. And then long term, a number of the people that are in this field are interested because of AI. Or is neural nets AI? No. Will neural nets help us get to AI? Maybe. And I think you also have to ask yourself, well, how do you define AI and what does that really mean to you? Because some people would say we have AI and we have them with neural nets. A lot of those who I have heard speak would say it's not there yet and not what we typically would expect. And if you're thinking like the Terminator or Her or HAL, we're definitely not there yet. But I think to get us down that path, the interesting areas that some of the more experts in the space are focused on is the unlabeled data. Being able to find patterns, make predictions on data that doesn't have labels with it. Or even if you look at labeled data, being able to find patterns that we've never seen before, because there are so many patterns and things to see in this world that a human can't necessarily interpret. And so finding those kind of patterns, I think, is really exciting to those who are in the space. And they're finding ways to it, but it's not as commercially baked yet in terms of what that means. It can be a little scary, I know, but I find it exciting. I ended this on my last talk, and I'm going to kind of end it with this as well. When I was doing this talk, or practicing this talk in my room, I had my iPhone plugged into the wall. And every few minutes, it would decide to try to search on whatever I was talking about. And I kept thinking, it would be really great if my iPhone had enough knowledge and was at this level of complexity where it could actually listen to my talk and give me feedback. Yeah, scary, but kind of cool if you think about it. And I think we can see that through neural nets. I don't know when, I don't know how, I don't know why. I kind of know why, but I think it's more, I don't have a when is that going to come about, but I do think that they will play a role in that. And they're not going to be the only part of the solution, but they will be a real crucial part of that solution. So that's why I find them exciting and interesting and kind of want to keep exploring them. And if you find them exciting exploring them, I would say, don't let the complexity frighten you or keep you from diving in. Just be ready for doing a lot of research and a lot of exploration, because like I said, it gets really hard and gets really complex, but it's not impossible. There's a significant amount of research being done now, and a lot of stuff that's already been pre-established for you to get off the ground and get running. So my slides and the video from PyCon is on my site. I already talked about my GitHub in terms of where I have the neural nets examples for the MNIST. And then my company, SkyMind.io, we are 3 people right now, and we're really small. And we're really hopeful and scrappy and working hard, but you know, keep an eye out for us, because I think we can do some really good things. And that is all I got. So I really appreciate you guys listening, and I will take some questions as best as I can, and thank you again. All kinds of hands. Okay, go.
So for somebody who doesn't know this field much, right, and faces with a problem, is there a way to determine whether this problem is feasible? And is there an easy way to do that?
I think if you're going to really dive into this field, the problems that you're looking at, if you see problems that sort of map to, you know, image processing or language processing, those are going to be easier to say. It just depends on what kind of problem you're faced with, and then also how much data do you have. Neural nets are best suited for having a significant amount of data. How much is that? You know, there's only 60,000 examples in MNIST, so you know, it's not a lot of data. So you don't obviously have to have, like, you know, gigabytes upon gigabytes, but frankly, if you're really going to get serious about creating a valuable neural net in a commercial setting, you probably want to have several gigabytes of data. I would recommend, too, just looking at Kaggle. I think that's falling out of favor from what I've heard, but, you know, Kaggle's got some great examples of competitions where neural nets have been applied, and you can see sort of in what cases and what kind of data sets are out there that people have been using it for. Yeah, okay, good to know. MNIST will probably be around forever. We can never get away from it. So yeah, no, that's good to know. Anyway, so hopefully that will give you some sense of, you know, in terms of problems, there's a lot of research out there in terms of, like, what are good cases and why, and I would just recommend digging into it a little bit further. Let's see, I know I saw, yes? So Word2Vec is actually a type of neural net. It's not deep learning. It's a shallow net, but it's actually more like feature engineering in terms of coming back with features on the actual sentences or words, depending on what you're processing into it. It's turning those words into vector representations, digit representations that you can pass into the neural net. Yeah, so they are. Word2Vec is a neural net. And I know you had your hand up initially, too. No. And if it doesn't converge, you would want to look at the way the neural net is structured. There's a number of hyperparameters that you could potentially explore, adjusting in the neural net structure, adjusting in the way you're doing your learning. You know, there's like learning rate. I think especially when you're talking about converging, the optimization would be doing things around, like, the learning rate and the momentum. There's a couple of different hyperparameters to explore in that space. It just depends on the issue that you're hitting up against with the convergence, and, like, how you've currently got it, at what method you're using and what parameters you're applying. Does that help you, or are you? Yeah, sure. It kind of doesn't. It gives you a very high abstract, but it's hard to give concrete based on whatever the problem that you're trying to solve. There are some, I think there's a lot of research and papers that exist about whatever the type of problem you're trying to solve that will give you some recommendations on where to start in terms of, like, error rates and so forth, which ones to initially apply based on the structure you're using and the data set you're potentially applying it to. There's a little bit of from what they keep telling me, is that you get more and more intuition based on working with these types of problem sets, and you may just literally have to do a little bit of this and, like, kind of pick something at random and then start to tweak it. So, yeah. Wish I could give you more details beyond that, but that's what I know right now. Was there anything? Well, it is and it isn't. There's definitely some research that can give you some fundamentals to start with. You know, there's things like AlexNet, and that's not necessarily, it's a type of structure that you can use to get yourself off the ground for, like, image processing. And then the actual, you know, optimization methods. People will have actual like optimization methods that they've identified that are ideal for like if you're doing an image processing and what learning rate to start with and what activation or loss functions to use. So that information exists. It requires some academic research, but it's out there. All right, you've raised your hand? Yeah.
I recall you mentioning why the digits were reversed.
I know, because I said I wasn't going to say no. I explicitly avoided saying it just because it's kind of going down a, it's an example that exists on Jan LeCun's site. And I wanted, because as you noticed throughout the presentation, I was primarily showing you neural nets that were going from left to right. So I wanted you to see the example where it has the input and each layer is going from left to right and that it flows in that direction. Because if it flowed in the other direction, it would kind of go against your understanding that it all kind of maps. So his example flows in the other direction. So recurrent neural net would help you actually retain memory and state. That would be an example of a type of neural net that would allow you to keep that. Yeah. Yes. Yes. Are you talking about this guy? Yeah, so I've read that, an optimal structure can be like 7 layers, and that you would have 10 outputs because you're classifying for 10 digits. And then your inputs, like I said, it's a 28 by 20. Well, I said this actually with the computer vision example. I meant to say this for this, but usually your MNIST is a 28 by 28 image, so you'll have 784 inputs. And then the number of nodes in here, that varies based on the type of structure you're using. I've heard you could have like up to 1,000 plus nodes in like 1 layer. And your net based on the structure could actually go smaller and smaller, and probably will have smaller and smaller or less nodes per layer as you get into moving forward through the layers. It depends on the structure. It depends on what you're working with in terms of how many nodes you'll have in each layer. But yes, and as I was kind of mentioning, there are some pre-baked kind of foundational perspectives on like how many to start with, and then how to go from there. And there is some math, especially when you get into convolutional neural nets. Karpathy has a good paper about the math you would use to help determine sort of how many layers or how many nodes you would have at the end of a convolutional layer. So there's definitely some good equations out there that will help you, based on the neural net structure you're using, determine how many nodes in the layer. They're usually a convolutional neural net, and it doesn't have, not all of the layers are fully connected. You can do fully connected. It can take longer to train. So yeah, and it's harder to scale. Yeah, in convolutional, it'll look at like different areas of the picture. Each node will look at kind of different spaces and groupings of what's going on at different areas. And it's interesting. I saw like it'll prioritize in I think a 7/1, just that top bit that is the length of the 7 to help determine between like a 7 and a 1. That would be an example of a node focusing on like just the top half of the 7 and between a 7 and a 1 to determine between the two. Give you a little bit of an understanding? Great. All right, somebody else? Oh, so yes, Spark and Hadoop. Okay, so the question was, is there advantage to using Spark and Hadoop to do deep learning? And yes, there is, and there's definitely exploration going on with that. A couple of things I could mention. The packages that I mentioned, there's some of them that are actually set up to be used on GPUs, like there's an easy integration with it. I don't know, I suspect one or two of them probably are exploring how to integrate with Spark and Hadoop. My company is integrated with Spark and Hadoop. But yes, you can do parallel processing. Neural nets are really great. Most of them can be really great at parallel processing, and Spark and Hadoop allow you to do distributed computing and parallel processing and allow a faster turnaround time for training. So yeah. I don't know all the packages that integrate with Spark and Hadoop on the Python list, but I think some of them are exploring that. Yeah. Yes. Yes, that is. It's a great question. It's a whole nother talk. So I was asking, how does unsupervised learning work? And it's, yeah, it would take, it's a hard thing to explain. It definitely has a different way of calculating errors and figuring out like how to fix the weights. It's called like generative learning in terms of it's trying to take the data, and this is getting to feature engineering, frankly, but it takes the data and tries to see patterns in the data, and based on the way the data is being fed through and the way the math is working, is it literally the neurons take, like, you know, we're talking thousands of representations and starts to say, you know, I'm going to put weights here and look for this specific pattern. So if I'm looking at an image, I'm looking at this specific pattern, and it tries to reconstruct the data instead of it being like, I'm trying to check and see if this means, you know, X. And then yeah, I don't know, unfortunately, too much about the unstructured space yet. I'm still exploring it myself, so I can't fully answer that question. But there is some research out there, and there are models that exist that allow you to explore that space. It just isn't as, it's not as fully effective as the supervised learning space, and not as fully, I think, evaluated as the supervised space. But it's out there, for sure. Yeah. Yes, definitely. The neural nets could definitely be underperforming in respect to other classifiers, especially if the data set is small, doesn't have a lot of characteristics to it, a lot of features to it. You know, some of these data sets will make more sense with like linear regression, logistic regression. You don't need a neural net would be overkill, and I knew I was going to blank on examples because I had a feeling somebody might ask me about this, and I was trying to make sure I could easily grab an example off the top of my head. But, you know, I would say if you're doing stuff with like, I mean, you can do recommender engines, frankly, without a neural net. Some of them, the performance is actually pretty accurate and adequate for what you need without applying necessarily a neural net. And some people argue that the neural net that's in Netflix isn't necessarily providing that much more value than, you know, but there's definitely, I think you'll find that maybe some data sets will have a couple of just unique features that are very telling of what the data set is predicting. And if you only have like a couple of features that are telling, there's no reason to use a neural net. If if I had 3 features about a data, then there's no reason for me to go to a neural net. Or if there's not much layers to my features, if I'm looking at a person's eye and I can look at the color of the eye, but maybe there's the shape and some additional points beyond the shape that you can make more nuanced, and like a Russian doll of like, as you can break it down further and further. A lot of data doesn't necessarily have that kind of structure. And I'm really not going to be able to come up with the top of my head, for whatever reason, a good example right now. But if I'll think about it. Yes. So the question is, you know, in terms of AI, is it because that they're specific to the types of problems they're designed for versus being able to make them much more, you know, generative in terms of being able to come up with new patterns or new ideas that you haven't already kind of identified or helped it identify? Yeah, I mean, you know, I think there's different discussions around what is AI and like, is it human intelligence? Is it an intelligence that is beyond what we can comprehend? You know, but I think at the heart of kind of what you're asking, yes, that the current neural nets, the way they are working, is that they're able to solve for problems that we are kind of defining for them to a degree, and it's not necessarily able to kind of take that next logical leap in terms of, what's that? Adapt, yeah. And can we do that with neural nets? Different perspectives on whether we can or not. Yeah. He does. Yeah, he's got a Coursera course. He may have, okay, yeah, I was going to say, he has a Coursera course that's for machine learning, and he has about 3 classes that he focuses on neural nets. It gets, it's definitely in the math space, like very much focuses around the math of the neural net. So, you know, hopefully these terms will give you enough context to start to approach that. But I agree, it is a good explanation. And Jeff Hinton has a number of presentations that exist out there, also extremely high, like a lot of math, a lot of terms that are used. There's a number of others. Karpathy, I think, if you want to get into something and the math is maybe feeling a little overwhelming, Karpathy's got some great research notes, and also he has a class at Stanford that focuses on convolutional neural nets that I would recommend looking at, and I have that in my references. And I think I also have Andrew Ng's course in my references, and Jeff Hinton's. And yeah, this was something I saw on a slide that Andrew Ng had presented. So yeah, that's where that came from. Yeah, I'll put this back at the end in case anybody still wants this information about. There's my talk again. Anyways, yes. Okay.
One is somebody.
Okay. So he's asking about, and he's asking about the types of audiences that would be using neural nets, and whether you would need to have a real solid understanding of the math behind it. There's efforts in place to try to make this so that you don't have to have as much knowledge about the math. But frankly, from what I have seen so far, I would think that if you really are going to be diving into this and applying it to real-world problems, that you do have to spend some good time understanding the math that's behind it to be able to understand how to really tune it appropriately, as well as reading some of the research that's out there to see where to start so that you aren't just starting from scratch, that you're starting with, you know, looking at stuff that has come before and leveraging that to help you get off the ground and get running. Yeah.
They necessarily have idea to come up with
so, right. So the question being, like, if you're using these libraries, do you have to know, how much of do you need to know to really get off the ground with the libraries? Some libraries are definitely going to have stuff pre-baked for you. Other libraries, you will have to understand the math a lot better to be able to get them to work. Like I said, GraphLab kind of gets you off the ground and running, but even to be able to manipulate it and make it work better, you're still going to want to know the math to be able to sort of know what kind of changes you want to make to it to make it work more effectively. Yeah. I see a lot of people leaving, so if you have additional questions, I'll stick around for a little while. But again, thank you very much.